Hi everyone, today I will be walking you through my MATLAB program called the RootFinder tool. This tool allows users to input a function and apply different numerical methods to find its roots. Let's go step by step. First, we start by clearing everything out to avoid errors. Clear removes any variables from memory. CLC clears the command window and this line just prints a welcome message to the user. Here, we ask the user to type a function, for example, sin x minus x divided 2. We then turn the string into a real MATLAB function using str2 func. Now f acts like any other function. We make sure the function works by trying to evaluate it at x equals 1. If there's an error, we tell the user to check their input. Now we ask for the start and end of the interval, basically where to look to the root. Then we list all the root finding methods available. Each method has a number of user can select. Then this line display the methods to the user and let them choose one or more by entering like 2 space 3 space 6. We prepare the placeholder for the derivative, no options needed. If the user pick method 5 Newton-Raphson, we try to compute the derivative automatically. Then this block cleans the input and uses symbolic math to get derivative. Then it converts it back into the usable function. If the auto derivation fails, the user can enter the derivative manually. We still check if it works by testing at x equals 1. Then this is where the magic happens. We look through each selected method. We go through the user's selected method one by one. We make sure the method number is valid. If not, we skip it. Then we show which method we're about to run. Then this is where each method gets called. Each one is its own function and receives a function and interval and the derivative if needed. If something goes wrong, we catch the error and show a helpful message. Once all selected methods finish running, we take the user and end the program. That's it. This RootFinder tool makes it easy for users to explore multiple numerical methods by typing a function. Thank you. Hi everyone. Now I'm going to walk you through my MATLAB program that estimates roots using the graphical method. This is a sample and initiative approach where we plot the function and define where it crosses the x-axis. Now let's look at the code for our main function, graphical roots. This is the start of the function. We're calling it graphical roots and returns a list of estimated root values. It takes 4 inputs: fx, the function we're analyzing; interval, the range where we're looking for roots; points, and how many x values we want to check; and tolerance, how close to 0 a value needs to be counted as a root. These 2 lines are safety checks. If the user didn't give us values of points of tolerance, we assign the default values, 1000 points and a tolerance of 1e minus 6. Here, we generate the x values from the given interval using linspace, and then we input the corresponding y values by applying our function fx to each x using our array fun. Then we analyze 2 empty arrays. Root values will store the roots we find, and then summary data is optional. It stores information about how the roots were found, like endpoints and midpoints. Now we look through every pair of points in an X array. We're going to check if the y values change sign between 2 points. That's a clue that a root exists between them. These are the y values in the current point at the next point. This means there is a sign change. One y is positive, the other is negative, so the function likely crosses 0 between the x values. That means our root is here. We estimate the root is a midpoint between the x values and our results. We also store the info about this section for lagging or later review. Now if y1 is very close to 0, that means xj itself might be a root. This checks helps avoid duplicate entries when two roots are very close to each other. And again, we save it both to the list and root list in the summary. This prints a title in the console, so it's easier to read. Depending on whether we found roots or not, we display either a warning or the list of detected roots. These sections create a plot. We drew the function in blue and dash backline at 1 equals 0 to represent the x-axis. For each root, we put a red circle on the plot and label it with the root's value. So finally, we add a title, label the axis, show the legend, and turn a grid to make the plot easier to read. And that's it. This program is great for visualizing where roots exist and works well as a first step before trying more precise methods like incremental or Newton plots. Good day everyone. Today I'm going to present a MATLAB program that implements the bisection method, one of the simplest and most reliable numerical methods for finding of roots. We'll walk through the code I create step by step. Let's begin with the main function called runBisectionSolver. This line defines our main function. It talks in two inputs, func, which is the function we want to find the root of, and domain, the range of the values we want to search within. This prints a neat heading in the command window, letting the user know they're about to configure the method. Then this line asks the user to input three values: dx, for how many finally we want to scan for sign changes; epsilon, the accuracy we want in the result; max steps, the maximum number of steps to take during the bisection. Then this is where the real works begin. We pass all the inputs to the scan bisection roots function. We will scan the interval and try to find all roots using bisection. It gives us found roots, a list of roots it found, step log, all the steps taken, useful for displaying later. This part checks if any roots were found. If not, it tells the user. If yes, it displays them nicely in console. This calls another function to show a table of all iterations. The bisection method went through a great tool for analysis. And finally, we analyze the function and the roots found using a plot. This gives a user a complete clear picture of where the function crosses the x-axis. So that's our bisections script. It serves as a front end where the user interacts, and it collects all the helper functions together. Now let's move on to the subtrunking that actually do computations behind the scene. Hi everyone. Today I'm going to walk you through my MATLAB code that implements the regular fallacy method to find the roots of function. Now, not only does this method find one root, it can find multiple roots within a given interval by scanning its segment step by step. Let's start with the main function called regular false roots. This function is responsible for finding and displaying all the roots, along with the detailed iteration tables and the graph. This line defines a function. It takes a function g and a search interval like 0 and 10. It returns the root we find. These are the parameters. Delta is the step size between segments. Threshold is the error tolerance. And max steps is the maximum number of iterations per root. This line calls another function that scans the interval in chunks and applies regular falsi to each segment where root net exists. It returns the list of the roots and the iteration details. This part prints the set of info like the interval, step size, and tolerance, so we know the parameters we use during the search. Here, we print a nicely formatted table, showing each step of regular file share process, including A, B, C, the error, function values, and the segment number. Now, we generate x values between our interval and compute their corresponding y values using our function g. This plots the functions in magenta with a thick line. This adds a horizontal dash line at y equals 0 so we can clearly see where roots are located. This loop plots each found root with a colored marker and label. This function scans a full interval, dividing it into small segments using the delta we set earlier. This loop keeps checking segments from the lower bound to the upper bound. If the signs of function values change, or the one value is very close to 0, we know it's a root in this segment. Then we call the regular file mode onto this segment. This function performs the regular file method is the single abrow. This calculates the relative error between iterations to check for convergence. If the error or the function value estimated is small enough, we accept this is a root. Based on the signed result, we update our bracket for the next iteration. And that's all for the bicep for the regular file method. Hi everyone, today I will be walking you through the incremental search method using MATLAB. It's a simple way to find where function crosses the x-axis, which means we found the root. Here, we print the summary, the interval we search, the step size, and any roots we found. If no roots are found, we print message, otherwise we show how many roots were found in their values. If we have data, we show it to the step-by-step table, makes it easy to see how we found the roots. We create the x values across the interval and calculate y values using the function. And then we plot the function in blue and draw the x-axis as a dashed line to show where the roots might be. Then if the roots were found, we mark them as dots in a graph and label each one. We add a title and label the axis and turn on the read to make the graph easier to read. This is the helper function that does the actual root search and step logging. We go through the interval step by step, checking 2 points at a time, and the function changes the sign between 2 points. A root is in between, where the quarter bin point at the root. Its details, x values, fx, product, and whether a root was found are stored in a log. And that's it. The incremental search method helps us find roots by looking for sign changes. It's simple, visual, and works well when you don't need super high precision. Thank you for listening. Hi everyone, today I will be walking you through the near-option RootFinder code in MATLAB, line by line in a simple and friendly way, so let's get started. We're starting with a function called Newton roots v2. It takes the three things a function func, its derivative deriv, and interval where we want to search for roots. Next, we define a few settings. Tolerance is how close we want to get to the real root. Increment controls how often we try new guesses, and max iteration is just a safety cap so we don't loop forever. These lines just prints out a nice summary for our settings, the interval and the size and the tolerance. Here we call a helper function to actually do the hard work. It returns the list of the roots in found and table of all the iteration steps. This part checks if we found any roots. If not, we say so, otherwise we print each root nicely one by one. Now for the fun part, plotting, we generate x values across the interval and compute the y values using our function. We open a new figure, hold it, and draw the function in blue. We also draw a dash horizontal line to represent y equals 0, and that's where the roots are. This colorful part puts a marker on each root we found and label it with its value. We use a different color for each root to keep things changed. We finish the plot with the x-axis label, a title, and a helpful legend that lists all the roots. We turn on the green for easier reading. So finally, if we have iteration data, we format it to the new table and show it. This helps us to see how the method arrived in each root step by step. This function confirms that actual new options method starting from one guess. It keeps updating until it converges or reaches the max steps. This one scans the interval using multiple guesses and collects all unique roots. It also keeps a full log of the steps for each guess. This tiny helper checks if the newly found root is far enough from existing ones to avoid the listing duplicates. And that's it. This is the whole program. It's powerful, but it not only finds all the given range but also logs the journey, visualizes the roots, and prints everything out clearly. Thank you for listening. Hey everyone, I'm going to explain this MATLAB program that finds roots of a function using a second method. I'll walk you through each part of the code in a simple and friendly way, so you can understand how it all works. We start with the function name find second roots. It takes two inputs, found where is the function we want to find roots for, and domain, which is the interval we research for those roots. Here we set up some important parameters. Tolerance tells us how close to zero the function value should be for us to call it a root. Max steps limits how many iterations we'll try before giving up, and increment decides the step size we use to scan the domain. We print out this setting so anyone return the code can see what parameters are being used with the root search. This line calls a helper function named detect all second roots, which does the actual work for scanning the domain, running the second method multiple times, and collecting all the roots it finds along with the detailed iteration data. Next, we check if any roots were found. If not, we tell the user no roots were detected. Otherwise, we list out each root found, one by one, with 6 decimal places for clarity. This prints such a header row for summary table showing the iteration step of the second method. This table includes starting points, iteration counts, function values, the new estimate, and error percentage. Here we look through all the recorded iterations and print their details in neat columns. If the error is not available, we print a dash instead to keep that table tidy. Now we create a plot to visualize the function over the domain. We drew a function in root and red and add a dash horizontal line at y equals 0 to mark the root axis. We mark each root in a plot with a colored circle and label it with the root's value. Each root has a different color to make them easy to tell apart. Finally, we add a bold title, label the axis, and add a legend that shows the root labels, and turn on the green to make the graph easier to read. This function scans the entire domain by splitting it into smaller segments defined by gap. For each pair of points, it runs the second method once, collects iteration logs, and adds any root found to the set, making sure to avoid duplicates. This is the core second method loop. We start with the two initial guesses, calculate the next guess, compute the relative error, and record every step. If the error is small enough, we declare we found a root and stop. If the loop ends with a convergence, we return the last guess. This small helper makes sure each root we add is sufficiently different from those already found, avoiding duplicates that are close together. This function works to scan, compute, log, and visualize all roots of a function in a given interval using the second method. The program prints detailed iteration data and plots the function with the roots markers, making it easy to understand the root finding process. And that's all. Thank you.